Let's sort numbers. So we want to give algorithms for the sorting problem, and the sorting problem is as follows. The input is a sequence of numbers, and the output should be the same numbers, meaning a permutation of those numbers, such that the smallest comes first and so on, or more generally, the first one in the new order is smaller or equal to the second one, and so on. As in this example, I have a sequence of numbers, and the output contains the same numbers, but sorted in increasing order. I say sequence here. Generally, we assume that the data, the input is given as an array or a Python list. Also, if you think of applications of the sorting problem, typically with the number there's some additional data and the numbers are just keys. So you could imagine you want to sort files by their size, and what you're actually sorting is your files, and the number, the file size is just the key by which you are sorting. So you might have additional data, satellite data stored with your keys, but we reduce this to the kind of basic problem of sorting numbers. So from now on, we just have numbers and we want to sort those. And there we're going to see several solutions to this problem, so different algorithms for sorting. So before I continue, you might want to pause the video and for yourself think about, given a sequence of numbers, how would you approach the problem of sorting them? You hopefully have come up with some idea to sort. Let me start with the possibly simplest idea for sorting numbers, and the corresponding sorting algorithm is called selection sort. And what is the idea of selection sort? So I have a sequence or an array of numbers, and what I do first is I find the smallest number. So the smallest number is 3. I place 3 in front. Then I find the second smallest. The second smallest is 7. I place the 7 next to the 3. And so on. And eventually my array will be sorted. So how do I find the 3 or the 7 or the 9? I do so by searching the array, meaning I go through the array, I find the minimum and move it to the front. How can this look like as an algorithm? So my loop goes from 0 to n minus 2, so not up to the last element. We'll see in a moment why, or maybe it's already obvious. We set smallest to I, so we want to find the index of the smallest number, and we initially set that simply to 0, or the smallest remaining number, and then we have a loop over all numbers with higher index, so starting at I plus 1 and going up to n minus 1, so going up to the end. And if that number is actually smaller than what I currently have stored as the smallest remaining number, then I set the index, or set the variable smallest to j, so to that to the index of that number. And then if I've done so, if I've run through all of the array, I then set a I to a smallest. So initially, so I would set I to 0, so it points at the 12. I go through the array finding the smallest number and setting smallest to the index of that number. That would be in this case 0, 1, 2. Then I swap a0 with a2, so the 3 goes here, the 12 goes there, and then I do the same on the remainder of the array. So initially So I is now 1, so I have the 9 here. I find the index corresponding to the smallest remaining number, that would be 7. I swap the 7 here, the 9 goes there, and so on. This is selection sort. How do we prove correctness of selection sort? That would be a loop invariant proof. I will not do that here, but that could be a nice exercise for you. Actually, so we have an outer and an inner loop, so you would want to do possibly a loop invariant proof for the inner loop first, and then use the loop invariant from that for your loop invariant of the outer loop. What is the running time? Yeah, have a look at this algorithm, because now I'm going to make this a quiz. What is the running time of selection sort? Is it order log n, order n log n, or order n squared? And again, we would like to have a tight bound. The correct answer is order n squared, and you can see this simply by going through the algorithm line by line, summing up according to the loops, and then essentially you end up with a arithmetic sum or arithmetic series, and this gives you then order n squared. Insertion sort. So one way to explain insertion sort is by looking at how would I sort a hand of playing cards. And one way of doing this, and that would correspond to insertion sort, I start with an empty hand, then I pick up cards one by one, and I always try to place them on the correct position. Meaning, I pick up a new card, I compare it to the largest card that I have so far. If it's large, I just leave it where it is. If it's smaller, I compare it to the next largest, and to the next largest, and so on, until I find one that is smaller, and then I place it there. And so on. So I compare this to the largest, next largest, it fits here, and I am done. So to find the position, I compare, in this case, from right to left. And what I use as loop invariant is that my hand so far is sorted. So the idea is I have a partial solution. I have the solution for all cards that I've seen so far. And now I'm inserting a new element, and that is then called an incremental algorithm. Insertion sort works well on small inputs. So if I only have a few numbers to sort, it's fast. It is an incremental algorithm, meaning that I process the input elements one by one, always maintaining the solution of whatever I've seen so far. So generally speaking, before talking specifically about insertion sort, what an incremental algorithm does, so we're processing the elements one by one. In pseudocode, this could look like this. I first initialize the algorithm with some kind of solution on, let's say, one element. So I have elements from x0 to xn minus 1. So then I would initialize the algorithm by computing the solution for x0. And then for all remaining elements, I compute the solution up to xj by taking the solution up to xj minus 1 and inserting xj into that solution. So what does that mean for sorting? I start with one number, one card, and that I sort that card. I mean, one card is always sorted, so I'm fine. Then incrementally I add more and more cards, so I sort everything up to j, making use of the fact that everything up to j minus 1 is already sorted. And the way of doing this would be the following. We're currently looking at aj and want to know where to place aj. So we're doing this, we're setting key to aj, and now we might want to move it forward. Therefore, I'm going to set I to j minus 1, so that would be kind of the first position to check where we could place aj in case that element is larger than aj. So as long as we haven't reached the start of the array yet, which corresponds to I, as long as I is larger than minus 1, or larger equals 0, and as long as the element that I see is larger than the element that I want to insert, which is the key. I'm going to move the element that is at AI to AI plus 1. And I'm going to decrease I by 1, so I go one card forward. All of this happens in this while loop. When I'm done with the while loop, I know where I want to place my new element, namely at what is currently AI plus 1, and I set that then to the value of the new element, which is key. What happens here, I have the 6, which I want to insert. I set I to j minus 1, so j minus 1, it points A of I is 28. Since I'm not yet at the start of the array, and because 28 is larger than 6, I'm moving the 28 here. And likewise, I'm moving the 17 here, and then I'm moving the 14 here. And then this is my current I, and 3 is smaller than 6, so I stop. And at the point where I stop, now this one here is I plus 1, and I place the 6 which I stored in key, I place that on that position, and that is insertion sort. One property of insertion sort is that it's an in-place algorithm. So what does in place mean? It means that we essentially do all of our computations in the original array. We only use a constant amount of extra memory. So we need some extra memory to store I, to store key, but essentially everything that we're doing is happening in the original array, and we're not allocating, let's say, another array of the same size or anything that is larger. So that is called in place if we only use constant extra space beyond the original input. Also note this initialization here for A0 we don't really need, as in A0, I mean a single number is already sorted, so we can skip that line from now on. How do we prove correctness of insertion sort? We have a loop, we do a loop invariant proof. The loop invariant that we use is at the start of an iteration of the outer for loop, indexed by j, so j is the index of the outer for loop. The subarray from A0 to j, so that is not including j, consists of the element originally in that subarray, but now sorted. So that is our loop invariant. It's a loop invariant for the outer for loop, so this loop here. We start with initialization. Initially, j is 1, so A0j is just the first element. So if I take the array that only includes the first element, and naturally because it's only one element, it's sorted. So initialization works out. Maintenance. Strictly speaking, I should say what the while loop does, but let's simply assume that it correctly moves elements to the right until I can insert the new element. If we assume that, then actually for maintenance there's not so much to prove, because if previously everything was sorted, then moving everything that is larger than my current element by 1 and placing the new element there again gives me everything sorted, because I have here the elements that are smaller. Here I have my new element. So this was my original AJ. And then here I have the elements that are larger. And because this part was sorted, and because this one is on the right position, and because that part remains sorted, it's overall still sorted. So that's maintenance. Termination. Termination, we should see what happens after the last iteration. So after the last iteration, so in the last iteration, j is n minus 1. So after the last iteration, j is n. So if I plug in n into the loop invariant, so I do n, here I do n, what does it say? It says that the subarray from 0 to n, which is all of A, consists of the elements originally in that subarray, so originally in A, sorted. So in short, we've sorted A. insertion sort is correct. Let's have a quick quiz. I said that insertion sort is in place, but what about selection sort? Is that also in place? Yes or no? Correct answer is yes. I mean, if you think about what selection sort did, it also only worked on the array itself. It didn't need to allocate extra memory except for a couple of variables. Let's analyze the running time of insertion sort. And what I want to do now is I want to have a tight bound on the worst case running time. I'm giving you a lower and an upper bound on the worst case running time. So for the upper bound, we just count the number of elementary operations or give upper bounds on those numbers. For the lower bound, what I do is I'm going to give a bad input and show that for that input, the algorithm needs a certain amount of time. So let's start with the upper bound. So we go through this line by line. Initialization, I mean, we already said we can skip this line, but in doubt it takes constant time. Now in the loop, we have constant time operations here. Then we have the while loop, and inside the while loop, this is constant time. We do this at most j times. So at the end, we still have something constant. So we get the sum. If I sum over all of those loops, I get the sum from 1 to n minus 1. And this is essentially order j. So here, this is now again the arithmetic series. And the arithmetic series is order n squared. Just as a reminder, the arithmetic series, so I have the sum j from 1 to n, j. This actually is n times n plus 1 divided by 2. And this is, of course, order n squared, because we have an n times n here. And this is what we were using here. The lower bound that we get here is also n squared, meaning that I have shown that the worst case is n squared. So the lower bound here is not best case lower bound. So in the best case, this algorithm might be faster. But for worst case inputs, this algorithm takes quadratic time. Why is that the case? Let's have a quiz about that in a moment. But what we can conclude, if that is the case, is that the worst case running time of insertion sort is quadratic. So what is the worst case input for insertion sort? Is it if all numbers are the same, or if the numbers are already in increasing order, or if the numbers are in decreasing order, or if the numbers are in random order? So the worst case input is if the numbers are in decreasing order. Why? Because when I want to add the jth element, it is the smallest of all of the numbers that I've seen so far. So I have to swap it forward up to the first position, and then the next one again, I will have to swap it forward up to the first position. So I always do j minus 1 swaps. So random order is not much better. It's also order of j swaps, but it's not the worst case. If it's in increasing order, what we actually have is that the new element is immediately on the right spot. So then insertion sort actually takes linear time. So the best case is actually better. Likewise, if all numbers are the same, that is just like the setting of an increasing order. But with a decreasing order, we take quadratic time. So the worst case quadratic bound is tight. We've seen two sorting algorithms by now, both running in quadratic time. So the natural question is, can we do better? And yes, we can. And an example of this is merge sort. So merge sort is a recursive algorithm, and more specifically, it's a divide and conquer algorithm. So what's the idea of divide and conquer? So divide and conquer is based on the idea of splitting the problem or dividing the problem into sub-problems that are smaller instances of the same problem. So again, let's say I have some numbers. I can split them into two parts, both of size n½ if I had n numbers. Now, conquer just means that I recursively solve these subproblems. So meaning that magically I can assume that my two subproblems are solved, or not magically, recursively, which also means that I need to define a base case. And then in a combined step, I combine the solutions to the subproblems to a solution of my original problem. So here I have two sorted sequences, which I now need to combine to one sorted sequence. Combine in this case it means merging, and that's why it's called merge sort. So once more in general, how does a divide and conquer algorithm look like? I need a base case. So if I have sufficiently few elements, or maybe just one, then I compute the solution for that small problem. I say here brute force. Often enough it's simply trivially. If I just have one element as such, for instance, is simply sorted. Otherwise, so for general n, what I do is I split the problem into two smaller subsets. Let's call them A1 and A2. I recursively compute the solution to one, the solution to the other, and then I compute the solution for the big problem by combining those solutions in a suitable way. What does that mean for sorting, and what does merge sort do? If only one element is left, then I compute the solution for one element. I mean, if I only have one element, there's nothing to do. Otherwise, I split into non-empty subsets, two of those, and run merge sort on both of those, and then I need to combine those solutions. So more specifically even, merge sort does the following. If I only have one element left, I do nothing. Otherwise, I copy the elements of my array to two arrays of half the size. So the first half of my array I copy to A1. The second half I copy to A2. Then recursively I call merge sort on A1 and merge sort on A2. And then at the end I need to combine the solutions. So how does this look like? So I have here my array. I split it into two halves, or I make copies of the two halves. Then recursively I do the same. So on A1 I now again get a new A1 and a new A2. And on the new A1 I get again a new A1 and a new A2, but these are now single elements. Those I now need to combine again. So I merge them. Likewise that A2, and so on. But all of this we don't have to think about, because that's the beauty of recursive algorithms. What happens down here we don't really care about. The only thing that we need to care about is, given that I have now two subproblems sorted, how do I combine them? So how do I do this last step? Everything below that will simply be solved by the recursion. I don't have to think about. I just have to think about, how do I go from, in this case, 1, 3, 14, 17, 28 and 4, 7, 8, 21, 35 to a merged list or merged array of those two. So how does merging work? Let's say I have A1 and let's say I have A2. How do I merge? I just start at the start of A1 and at the start of A2. And whatever is a smaller element, I will place that at the beginning of, or at the start of A1. So I have 1 and 4. The 1 is smaller. I place a 1 here. Then in A1, I go one step to the right. So I see the 3. I'm comparing 3 and 4. 3 is smaller. I place it there. I go 1 to the right. 14 and 4. 4 is smaller. So I place a 4 here. And so on. So we have described merge sort. Now we should look at correctness and the analysis of the running time. I want to do this only briefly. So very briefly, how would we show that merge sort is correct? So first of all, merge sort is a recursive algorithm. So what we're going to use, or what we would use, is strong induction, and strong induction in a very specific setting, namely in a setting where the induction hypothesis says the subproblems, the smaller subproblems, are solved correctly. So we would have to handle a base case. A base case is single elements. Those are always sorted. And then assuming that the subproblems are solved correctly, we need to prove that the overall problem is solved correctly. Meaning that assuming that the two lists that we get here are sorted, that the merging procedure merges them correctly. For that, we would need to define the merging procedure more carefully, and then, so that would be some kind of loop, and then use a loop invariant proof to prove that the merging is correct, and that would then overall prove that merge sort is correct by strong induction. Before talking about running time, let's have a small quiz. Very simple. We've seen insertion sort is in place. We've seen selection sort is in place. How about merge sort? Is merge sort in place? Yes or no? The correct answer is no, because what we did was we took half of the elements of A and copied them to an array A1, and half of the elements and copied them to an array A2. Now you could wonder, is that really necessary? So we sort them in A1 and have them sorted in A1. We have sorted them in A2. We want to merge them to one big list, and that is very difficult to do in place. So merge sort is not in place. Let's talk about the running time of merge sort next. So here we have merge sort, and what we can do is we can simply go through merge sort line by line and see how long that takes. So the first part takes constant time, so the base case we spend constant time. Otherwise, in the else case, okay, we first set n to some value, n1 and n2 to some value, so that is just constant. But then the copying takes linear time, so we copy the first half to A1, the second half to A2, so both of that takes linear time. The merging, if you think about what the merging does, the merging also takes linear time because we have the two sub-arrays, and then we go, we always take the smallest element of the remaining elements, place it in A, and then move one on. So essentially we look at every element once. We're looking at a linear number of elements, so that takes linear time. But then we have these two lines, merge sort A1 and merge sort of A2. How do we deal with those? So if we define the running time of merge sort to be T of n, or the worst case running time to be T of n, on an input of size n, then what we're doing here is we're calling the same algorithm on an input of size n half. So if T of n is the running time on n elements, then on n half elements we get T of n half. In this case, once rounded down, once rounded up. So when we have a recursive algorithm like merge sort, the running time analysis leads to a recursion or recurrence, meaning equation like this. So the worst case running time of merge sort, T of n, it's constant if n is 1, so that's the base case, but it's the running time on A1, which is T of n half rounded down, plus the running time on A2, which is T of n half rounded up, plus the linear amount for copying and merging, if n is larger than 1. So this is a recurrence. So when we write down our recurrence, we often will omit the base case, so we just write this second half here. Also, whether we're rounding down or up doesn't really matter, so this part here we simply write, so we have T of n half plus T of n half, so that is 2 times T of n half, and of course we still have this plus theta of n here. So in short, we will write this recurrence as T of n is 2 times T of n half plus theta of n. So we're spending linear time plus 2 times the time it would take to solve a problem of half the size. So this doesn't yet tell us the running time of merge sort. Let me tell you what this solves to. it solves to T of n is order n log n. And we'll see that in a later video, how to solve recurrences and how to figure out that this is n log n. But just to put this into context, n log n is much faster than n squared. So this is a much more efficient algorithm than insertion sort or selection sort. Just as an illustration, let's compare insertion sort and merge sort, and I've made up some constants here. So let's assume insertion sort is very fast in the sense that it has kind of very small numbers here, while merge sort has big numbers, which is somewhat realistic. Then, of course, for small n, insertion sort might be faster, because it matters more that there's a 15 here relative to the 300. But the larger n, the more the growth rate will play a role, and the more merge sort will kind of show that it's faster. And here in this example with 1000, it's already 5 times faster. But if we take 1 million, it's already 2,500 times faster. The larger n, the larger this difference will become. So merge sort is a much better alternative to selection sort and insertion sort because it's much more efficient. To see that, we need to be able to solve recurrences, and that's why in one of the next videos we're going to see how to solve recurrences. To wrap up, let's see which algorithms we've seen and what their properties are. We've seen selection sort, which runs in quadratic time. It is in place. Insertion sort is also quadratic time in place. Merge sort was order n log n, which we still need to prove, but we have the recurrence. It is not in place. So that is what we've seen so far in terms of sorting algorithms. We will see more in the future, but that's all for now. Let's end on a quiz, and the quiz is the following. So here I try to combine insertion sort and merge sort in the following way. Instead of the merge sort base case of if I end up with one element, I do nothing, I instead have a base case where I say if there are only 300 elements left, I will call insertion sort on the remaining subproblem. So what is the running time of this algorithm? So of this mixed sort overall. Is it n log n or n squared? This algorithm runs in order n log n time, and the reason being that the expensive part, so the insertion sort, only happens in the base case. And in the base case, we will have a constant number, even if the constant is 300, a constant number of elements left, so it doesn't matter what we do. The running time is dominated by what do we do for the large n, and there essentially we're doing merge sort, and that's why the running time is order n log n, which so far I have only claimed, so we'll have to wait for a future video to solve the corresponding recurrence and actually prove that the running time of this solves to, so that T of n being 2 times T of n half plus order n, that this solves to n log n. That's all for today. See you.